So what I'm going to talk about here are continuous probability distributions. So before we had discrete probability distributions, so just as a reminder, we had discrete versus continuous. So for example, discrete might be number of hippos in my house, and continuous might be the weight of a hippo. So what that means, for example, the number of hippos in my house maybe ranges from 2 to 17. And it's going to be a whole number. So there's no possibility. So if I say, can there be 4.1333 hippos in my house? The answer is no. We cannot. So it's a discrete variable. There's not an infinite number of options. This is different than the weight of a hippo. So the weight of a hippo, I actually have no idea, of course. But let's say it's between 400 and 3,000 kilograms. And so my question is, can it be 712.133 kilograms? And the answer is, of course, yes, it can. And could it be 1,012.245? And the answer is, yes, it can. And so there's a finite number of numbers here, and there's an infinite number of numbers there. To be more explicit about it, the number of numbers between 0 and between 1 and 3 is also infinite. There's an infinite number of numbers between 1 and 3. Okay, now why does that matter? So let's say we have a probability distribution. So let's say let's say we know, for example, that our hippo weighs between 400 and 3,000 kilograms. And I say, what is the probability that the hippo weighs 712 kilograms? And the answer is, I mean, it might be tempting to say, so 3,000 minus 400 is 2,600. So it might be tempting to say that the answer is 1 out of 2,600, but that would be wrong. Oops, you missed my beautiful red X. The actual answer is that the probability is in fact 0. There is no chance that the hippo weighs 712. And in fact, there's no chance that it weighs any weight. If I said, what's the probability, right? What is the probability that what is the probability that it takes exactly 1 minute to drink a cup of water? So if I said, what is the probability that it takes exactly 1 minute to drink a cup of water? And let's say that the range is it probably takes anywhere from half a minute to 7 minutes to drink a cup of water. So what's the probability it takes exactly a minute? The answer is, again, 0. Because there's an infinite number of possibilities here, so the probability of it being one thing is, in fact, 0. We sometimes show continuous probabilities as a graph. So what we have here is we have the probability, and then we might have something like this. And so what that's saying is this is the higher the peak, the higher the probability. So let's say this was, I don't know, the length of a hair on a head. Right, so there's a lot of hairs at this length and at this length, but they could be at any length. And if I said, what's the probability of it being a certain point, the answer is, we have no idea. And in fact, so there's many different types of distributions. There's something called the Poisson, I think that one's called, and then this is called the normal distribution. Oops, that fell off. There's a right skew and a left skew, and there can be I don't know, a bimodal. That might be, for example, heights, right? Because, you know, women are around a height and men are around a different height on average. Probably for Mayfield, that peak would be higher. But there's different probability distributions. Now, the key thing about probability distributions is that we say that the area under the curve is equal to the probability. So if this is my probability distribution and it ends there, and I take the area of this entire curve, the area is 1. It's 100%. So when you have a probability distribution, the area under the curve represents the probability. So let's say, for example, I say, what is the probability of it? Let's say let's say I have a variable and this is going between 82 and 87, and I say, what's the probability it's 86? And the probability that it's equal to, that x is 86 is, of course, 0. And we could show that because the area of a line is, in fact, 0. And the probability of any number is 0. But what we could say is that there is a, if I say what is the probability that, like let's say I want to know what's the probability that's between 84 and 86. So I want to know what is the probability that the variable is between 84 and 86. My handwriting's falling apart. That is this area over here, this blue area, and that is not 0, whatever it is. So this area is not 0. So the area of it being exactly 86 is 0. The area of it being between 84 and 86 is not 0. Now what we're going to focus on in this unit, depending on how far I get, is something called the normal distribution. And it's called a normal distribution, I think. I'm not sure about this because things are normally distributed like a normal distribution. Or maybe not. I don't actually know. I semi-made that up. But that's normal distribution. Another name for it you may have heard of is the, you may have heard it called the bell curve. Right? And it's called the bell curve because, you know, it looks kind of like a bell, you know, ding dong. So that's the bell curve. But we're going to call it a normal distribution. So there's many different types of distributions. This is a normal distribution. And what's some features of the normal distribution are that the mode of the normal distribution, so the most probable result, is the mean. So it's kind of symmetrical around the mean. And then we could kind of space it apart, and we're going to do it in terms of standard deviation. So this distance over here is a standard deviation. So here we're at mu plus a standard deviation, and here mu plus 2 standard deviations, and mu minus a standard deviation, mu minus 2 standard deviations, and so on and so forth. One property of the normal distribution curve, there's a formula for this, by the way. You absolutely, of course, do not need to know it, but the formula is 1 over sigma root 2 pi, this is the real one, e to the minus 1/2 x minus u over sigma squared. That's the standard deviation. That's normal pi. E is a number, some of you may know it, it's 2 point something, 71 I think. And this you may or may not remember is the formula for z squared, but this is actually the equation for this. But yeah, you don't have to really know that. You don't have to know that at all. Okay, so back to our normal distribution curve. So one property of the normal distribution curve is that 68% of the population of the distribution is within 1 standard deviation of the mean. And similarly, well, not similarly, in addition, 95% of the population is defined as being within 2 standard deviations of the mean. And I didn't draw it on this thing over here, but if we actually did it, 99.7% is within 3 standard deviations of the mean. So if 68% is between there and there, and 34% is there, 34% is there. And then if 95 is there, 95 minus 68, 27 divided by 2, 13. So 13.5% is over here, 13.5% is over here, and then the rest is kind of in those tail areas. So 2.5%, and that's all the way to infinity, 2.5%. And that's a normal distribution. So that's how things are normally distributed. They are distributed such that most things are within 1 standard deviation of the mean. That's a normal distribution. So I'm going to stop there, and I'm going to say what we're going to do with that in the next video.